Direct variation. Direct variation is a relationship where as one variable gets bigger, so x, let's say x, gets bigger, then the other variable gets bigger, like y gets bigger. An example of what this would look like on a graph is if you had one thing get bigger, the other thing gets bigger. It has a positive slope. One thing that's also important about direct variation is that you always go through the point 0, 0. If you have nothing of one variable, then you have nothing of the other variable. The equation for direct variation is y equals kx. Now that k is called the constant of variation. We always want to find the constant of variation, so we can write a specific equation for any direct variation situation. And we can find k by dividing. If you look at our equation, y equals kx, if we were to solve for k, we would divide both sides and we would end up with k equals y divided by x. So those are sort of the steps we're going to look at as we look at some direct variation examples. We can write equations of direct variations from their graph by looking at the points that we can see. We want to be finding the constant of variation, and remember that y equals kx is the equation we're shooting for. So if we look at the first graph, I see that the point 1, 5 is on the graph. That tells me that when x is 1, y is 5. Well, we can use this information to help us find an equation. So 5 equals k times 1. Now you can see I plugged y where y was supposed to go and x where x was supposed to go. Now I can divide both sides and know that k equals 5. Which tells me this very specific equation for this situation, y equals 5x. And yes, you're looking at the graph going, I could have told you that. And you're right, this is a very specific example of a linear function with a slope of 5 and the y-intercept of 0, 0. So now if we look at our second example, we have a graph that goes through the point 2, 1. I know for sure it's direct variation. Well, I know that it can possibly be direct variation because it goes through 0, 0. And then the other clue to tell us it is direct variation is the fact that it has that constant slope. So we're going to use the point 2, 1. And we're going to find the equation for this. I'm going to plug in y where y is supposed to go and x where x is supposed to go. Now if we solve this one for k, we get k equals 1/2. And that is okay. Our equation would be y equals 1/2 x. Then we could answer all sorts of other questions about that situation. So, finding direct variation equations from graphs. Now let's look at finding direct variation equations from tables. Table is just a set of x's and y's that go together. It's just a set of points. So you could turn it into a graph if you wanted to, and then our steps would be exactly the same as on the last slide. If we want to know if something has direct variation, we need to look at every entry in the table. And for direct variation, we know that it is y equals kx. So we need every single y to be a multiple of x by the same multiple. So 2 to 10, 4 to 20, 6 to 30, 8 to 40. Is there a common multiple? They're all times 5. So this actually tells me exactly what I need for my equation. It's y equals 5x. This is direct variation because every single y is the product of the x and 5. Now let's look at this other table and see if we can fill in the blanks. We have the point 648, and we don't know any of the other points. If we know this is a direct variation, we can use our equation to figure out what k is. We can plug 48 where y is supposed to go and 6 where x is supposed to go, which tells us that k equals 8. That means the equation for this table is y equals 8x. Now we can use that to fill in the other blanks. When x is 2, y would be 16. When x is 4, y would be 32. And when x is 8, y would be 64, just by plugging it into the equation. Let's look at one last direct variation table. This time, the two we have that go together are 2 and 24. So, 24 equals k times 2. Divide both sides and we get k equals 12. So the equation for this situation is y equals 12x. We can use this to find the other blanks. Looks like when x is 7, we can plug that in, and that would get us y is 7 times 12, which is 84. Now, in the other ones, we're going to have to go backwards. We know y, so 48 equals 12x. Divide both sides, and you would get 4 for that blank. 144 divided by 12 is going to get us 12. So we can also find direct variation equations from tables. If y varies directly as x, and y equals 18 when x equals 36, we want to find the value of x when y equals 24. To do this, we need to find our direct variation equation. Now this example is a really important one because it says y varies directly as x. This will always be the order, even if you don't have x and y in your equation, even if it's something with temperature and speed and volume and all sorts of other stuff. As long as you remember y varies directly as x, it tells you where to plug things into your equation. So y varies directly as x. Now, if we look at what we're given, we know that y is 18 when x is 36. So 18 equals k times 36. Divide both sides and we get k equals 1/2. So now we can write the specific equation for this situation. Y equals 1/2 x. I always find the specific equation before I actually find the solution. That way I can double check myself. It gives me that in-between, intermediate step. And sometimes the equation is more important than the answer. So now we want to find x when y is 24. So let's use our equation. 24 equals 1/2 x. If we want to solve this, how do we get rid of the 1/2? We can multiply both sides by 2. How you undo a fraction. So x equals 24 times 2, which is 48. So let's start looking at some applications, since that's where we're going to see variation the most. The wavelength of a wave of a certain frequency varies directly as the velocity of the wave. So right away, remember, y varies directly as x. So the wavelength is the y and the velocity is the x. Alright, now let's continue on a little bit further. And the wavelength is 60 feet when the velocity is 15 feet per second. We want to find the wavelength when the velocity is 3 feet per second. Well, let's go ahead and write our equation first. Our equation is usually y equals kx. In this case, y is wavelength, so I'm going to use the correct symbols. So I'm going to use my wavelength symbol, lambda, which you should know from some of your physics things, equals k times velocity. Now I know that lambda, the wavelength, is 60 feet when the velocity is 15. So I can divide both sides and we can get k. This will give me k equals 4. So the equation for this situation is lambda equals 4 times the velocity. So the wavelength is 4 times the velocity. Now that we have this, we can use our equation to find the solution. Find the wavelength when the velocity is 3. So wavelength equals 4 times 3. So the wavelength is 12 feet. One of the things I like so much about direct and inverse variation is that there's so many physics applications. Here's another physics application. Hooke's law for an elastic spring states that the distance a spring stretches varies directly as the force applied. So, y varies directly as x. If a force of 100 newtons stretches a spring 5 centimeters, how much will a force of 368 newtons stretch the same spring? So let's go ahead and write an equation for this. We usually have y equals kx, since this is a varies directly problem. And in this case, we have distance varies directly as the force applied. So I'm going to use d equals kf so I can keep track of what goes where. So it says that a force of 100 newtons stretches a spring 5 centimeters. So 5 equals k times 100. Now we can divide both sides and we can get k. So in this case, k is going to be a decimal, which is OK. So k is 0.05, or 0.05 if you like that better. That means we can write the specific equation for this situation. Y equals 0.05. Oops, not y. What am I using? D equals 0.05 F. Now that I have this equation, I could answer infinitely many questions about this particular spring. However, I only care about the distance that my spring will stretch if I use a force of 368 newtons. I'm going to plug this into my equation. I know F, so I'm going to plug in for F. D equals 0.05 times 368. And this is where we whip out our calculator and we go, okay, 0.05 times 368 gets us a distance of 18.4 centimeters. So, more force, that meant further distance, which makes sense. As one thing gets bigger, the other thing gets bigger. Direct variation doesn't always have to be with a linear function. We can vary directly with other things. However, the same basic template for an equation still holds. So in this problem, c varies directly as the square root of d. So let's think about what we normally have. We normally have y equals kx. That's just varying directly as x in the linear sense. So in this case, we're going to do c equals k times the square root of d. So all we're doing is substituting that in. Instead of being a linear function, we now have a square root function. So let's go a little bit further. It says c equals 6 when d is 16. We can still find k. So I'm going to plug those things into my equation. C equals 6 when d equals 16. So let's see, the square root of 16, we can do that much. 6 equals k times 4. Divide both sides by 4, so you get k equals 3/2, or you can write k as 1.5. So now we have our equation. Well, we have enough information to write our equation. C equals 1.5 times the square root of d. Now we can finish our problem. We want to find c when d is 64. So let's plug in. C equals 1.5 times the square root of 64. So square root of 64, it's going to be 8. So c equals 1.5 times 8. So c equals 12. So just because we weren't dealing with a linear relationship here, we could still use our direct variation formula. It's just this time we had to use the square root of d. Let's look at just one more example where with a different kind of direct variation. This is one we should be very familiar with. The distance a body falls from rest varies directly as the square of the time it falls. So y varies directly as x, but in this case it's the square of the time. So if we think about our basic template, we usually have y equals kx. In this case, we have distance, and distance varies directly not just as the time, but as the square of the time, so time squared. So now we have our generic equation. We can find our specific equation by looking at the information given. The ball falls 144 feet in 3 seconds. So we plug that in, we get 144 equals k times 3 squared. So that would mean that 144 equals k times 9. Then we would need to divide both sides. So you need to do 144 divided by 9. And we'll get k equals 16. So now we can write our specific equation for this situation. D equals 16t squared, which should be very familiar to you guys. Now that we have this specific equation, I could answer questions for this ball for any time that I wanted to, even after it landed, but of course my answers would be a little weird. However, we want to know specifically how far the ball has fallen in 7 seconds, I think is what the problem says. So let's go ahead and let's plug this information into our equation. 7 seconds is time, so D equals 16 times 7 squared. D equals 16 times 49. So get your calculator out. 16 times 49. D equals 784 feet. So if that ball has been falling for 7 seconds, it has fallen 784 feet. Longer time, further distance. Direct variation is just looking at a relationship between two variables where the relationship is a multiplication by a constant of variation. With direct variation, it always goes through 0, 0, and as we just saw with our distance and time, as one variable gets bigger, the other variable gets bigger.